Good morning. This is 12.2 in the Big Ideas Geometry textbook, Independent and Dependent Events. The essential question for today is how can you determine whether two events, so two things that are happening, or the probabilities that they happen, are independent or dependent, okay? So two events are independent when the occurrence of one event does not affect the occurrence of another event, okay? So a lot of times these will take the form of rolling a die and flipping a coin. Okay, flipping a coin has no effect on what number you roll in the die. Okay, or rolling the die has no effect on what head or tail you flip of the coin. So those would be considered independent events because you can do them in any order pretty much. Doing one first doesn't affect how you do the other one. Okay, dependent events is when the occurrence of one event does affect the occurrence of the other event. Okay, so if you're drawing something out of a bag, and if you're drawing names out of the bag, and you're not putting those names back in, let's say first prize might be $5, second prize might be $10, and the third prize might be $1,000. Okay? So if you have all of your names in the bag, you don't want to be the first or second one, you want to be the third one. Okay? So if your name is drawn first, that has an effect on your chances of getting that $1,000 prize. Because if your name is drawn first, you're out of the pool and you can't be put back in, you get the $5 prize, you're out of the game for the big money. Okay, so those would be dependent events because what happens in the first and second rounds does affect what could happen in the third round. Because because your name would not be an option for that. Okay? So determine whether the events are independent or dependent. Okay? Two six-sided dice are rolled. Okay, so you have two dice. And they're being rolled. Does the result of one affect what's going to happen over here? So like if you roll a 2 on this one, can you roll a 2 on this one? Well, yeah, of course you can. You could have 2 and 2. You can have one of any of these. Okay? So what happens with this first dice has no effect of what happens on here. So these would be referred to as independent events. Okay. The result of event 1 does not affect the result of event 2. So event 1 and event 2 in this case are just the rolling of the die. So event 1 is rolling die 1, event 2 is rolling die 2. Part B, 6 pieces of paper, numbered 1 through 6 are in a bag. 2 pieces of paper are selected one at a time. This is an important phrase right here, without replacement. So that means you don't put the first piece back. Okay? So you're not putting the first piece back. It's without replacement. This is what we're doing when we're drawing names out of the bag. We're not replacing them. So if you are replacing, that means every time you draw, every number has an equal opportunity. Because if you draw 3 and you put the 3 back, then you can draw 3 again. That would be an independent event. But in this case, if you select the 3, it is now out of the bag. You can't select it again. Which means the chances of drawing one of these other numbers increases. So for your first round, drawing a specific number has a 1 in 6 chance. Okay, so in the first round, it's like, I want to draw, what's the probability of drawing a 3, or 2, or 5? Well, it's 1 out of 6. So since you're not replacing it, in the second round, your probability of drawing these numbers would be 1 out of 5. That is a higher percentage. This is 0.167, this is 0.2. Okay, so the chances of you drawing a specific number go up. That makes this a dependent event. Okay? Because the chances of later things happening are increasing. You have a greater chance of that. Okay, so it's a dependent event. Okay, that's from 12.1. So let's look at 5. This is page 361. You roll a 4 on a 6-sided die and spin red on a spinner. Are they independent or dependent? Does the die have any effect on the spinner? Does the spinner have any effect on the die? And that would be no, these are independent events. Okay. Your teacher chooses a student to lead a group, and then chooses another student to lead a second group, and then chooses a third student to lead a third group. Are they independent or dependent? Well, whichever student is chosen to lead the first group, it cannot be chosen here. So again, if you're not chosen for the first group, your chances of being chosen go up for the second group. If you're not chosen for the second group, your chances of chosen go up for the third group. So these would be dependent events. The results of the first event affect the results of the second event and the third event. Okay, so here's the vocabulary where we can fill that in. Independent events, okay, so that is one event does not affect the occurrence, that's the word they use, of the other event. Okay, and then dependent is just kind of the flip of that. When these are the right words here. When the occurrence of one event does affect the occurrence of the other event. Okay, so that's independent, dependent. Conditional probability. This is the probability that event, this is from page 677 in your book, B, probability that event B occurs given that event A has occurred. Okay? So this is written out more as the probability of B given A. And its short term is like that. Probability of B given A. Okay? So the probability of independent events, two events A and B are independent if and only if the probability that both events occur is the product of the probabilities of the events. Okay, so let's go back to the die and the spinner. So let's say we have a 6-sided die and we have a 4-color spinner. What is the probability of rolling a 2, then getting something red? Well, these are independent events. One does not affect the other. The probability of rolling a 2 is going to be 1 out of 6. Okay? The probability of rolling a red is going to be 1 out of 4. Let's say the 4 colors are red, blue, purple, and black. Okay? Make a bruise with purple and black. So the probability of 2, this should actually be written probability of 2 and red. Probably should write it out like that, 2 and red. So probability of 2 and red is going to equal the probability of 2 times the probability of red. So that would be 1/6 times 1/4. You just multiply them together, you get 1/24, which is 0.04, around there. 0.042. So we've got about a 4.2% chance of that happening. Okay, so you multiply those two probabilities. Now, probability of dependent events. If they're dependent, again, it starts with probability of A and B. Now it's the probability of A times the probability of B given that A has occurred. This is that conditional probability. Okay, so the example they use here is from example 2. So we have a group of 4 students, including 1 boy and 3 girls. Teacher randomly selects one of the students to be the speaker and a different student to be a recorder. Using the sample space, determine whether the randomly selecting a girl first and randomly selecting a girl second are independent events. Well, we should know already, and I want you to not get caught up in these rules with this, what's going to happen. I found this a little confusing, honestly, myself. But to know that if you're selecting someone first and you're not putting them back in the pool, if you're not replacing whatever you select, it's going to be a dependent event. Okay, so these are going to be dependent. What they did is they made a list of the total outcomes. Okay, now they made it so there is only 1 boy in the group, so that makes it easier for them and our chances are a lot less. But if you have 1 girl, it could go girl-boy or boy-girl. And you have 3 options for each of those, so 6 total options if you only have 1 girl. If you have 2 girls, there's 6 total options. So what they did is they said, okay, we want the probability of it's girl and girl. Probability of girl and girl. So what's the probability of a girl? Probability of girl first would be 9 out of 12 because they have 9 times that girl was chosen first. The probability of getting a girl second is also 9 out of 12. Okay, because there's 9 times, there's 6 on the right and 3 on the left, where the girl is second. So the probability of girl first and girl second is, if you just look at this, it's something different. Don't look at these lines up here. Probability of girl first and girl second, there are 6 times that happened, the bottom 6. Okay, so they're checking, does girl first times girl second equal 1/2? And you're like, well, 3/4 times 3/4 does not equal 1/2, so they're not independent. Okay. Again, these numbers actually confused me a little bit. I was like, I don't like looking at the numbers. I like just thinking, okay, does this affect something happening here? So when we determine this probability, okay, what is the probability of getting a girl first and girl second? If you make a sample space, you can just count. Oh, that's half the time that happens. Okay. So how this works with the numbers, what is the probability of girl and girl? What are the chances of that happening? What is that actual probability? We know these are dependent events. These are dependent events. So we need the probability of a girl times the probability of a girl given that a girl has been chosen. So this is where we actually drop things down a little bit. So remember, we have 5 kids, we have 4 girls, 1 boy. So the probability of choosing a girl is pretty good. It would be 4, there's 4 girls, and there's 5, so it's 4 out of 5. Okay, so those are pretty good. Now what's the probability of a second girl? Now we're not replacing the first girl that we picked. So now for the second girl, I have 3 girls and I have 1 boy. So the probability of a second girl would be 3 out of 4. Okay? So 3 out of 4. This is not matching up with what they have. So if I multiply those across, I get 12 out of 20, which is 3/5. That is 0.6. Our sample space shows 1/2. I have to check on that and ask me in class on that one. I'm not going to spend the time right now. But I think it should be 0.6. There are only 3 girls to begin with. That's my problem. There are only 3 girls. There are 4 kids. There are 3 girls to begin with. So if that's the case, we have 3 over 4 for girl, the first girl. Now we lose a girl, so now we only have 2 girls and 1 boy. So we have 2 girls out of 3. Okay? So that'd be 6/12, which is the 1/2. There's 1/2. You got to have the right numbers in there. Okay? Determine whether events are independent. Explain your reasoning. You have 3 white golf balls and 2 yellow golf balls in a bag. You randomly select 1 golf ball to hit now and another golf ball to place in your pocket. Use a sample space to determine whether randomly selecting a white golf ball first and then a white golf ball second are independent events. So let's think of this without the sample space here, because sample spaces get pretty long and tedious. When you pick out your first golf ball, can you pick that same golf ball again? Are you putting it back, and can it be your second golf ball? Can the same golf ball be your first and second? Well, no, that's silly, okay? So these are going to be dependent events. And I would say something like the items are not replaced. That's kind of what you're looking for. That's the key thing. Are things being put back? Does everything have an equal opportunity every time you do this? Okay, so the items are not replaced. The results of the first draw affect the second. Okay, so let's practice this. What is the probability of having a white and then a white? White and white. Well, you have 3. Let's make sure I get my numbers right here. You have 3 white golf balls and 2 yellow golf balls in a bag. So we have 5 balls. So the probability of getting a white would be 3 out of 5 for the first time. Okay. Now for the second time, the second white, you've already picked the white out. So there's fewer whites in there. Now there's only 2 white golf balls. And now there's only 4 total balls here. So we get 6 over 20. That would be 3/10. That'd be 30% chance. You'd have a 30% chance of getting white and white. Okay. Your friend writes down a phone number down on a piece of paper, but the last 3 numbers get smudged after being in your pocket all day long. Try to get a hold of that friend again and get that number. You decide to randomly choose numbers for each of the 3 digits. Last 3 digits. Use a sample space to determine whether guessing the first digit correctly and the second digit correctly are independent events. So we have 3 digits, 1, 2, 3. Here's the first digit, second digit. They're not asking about the third. They want to know, does the digit you choose here affect what you can choose here? And they don't say anything about each digit is different, and they don't say you can repeat or anything. We're going to assume we can repeat numbers. So this first digit, it could be anywhere from 0 all the way to 9. Okay. The second digit could be anything from 0 all the way to 9. Third digit, same thing. They're not asking about the third, but it could be anything from 0 to 9. You notice what we choose here has no impact on what we're doing here. So these would be independent events. The occurrence of the first digit does not affect the outcome of the second digit. Okay. Now, what is the chance that you randomly pick the correct first digit? Well, you have 10 digits to choose from, so it'd be 1 out of 10. The second one, you have 10 digits to choose from, so that'd be 1 out of 10. So that'd be 1 out of 100 to get the first 2 digits right. If you do the third one, you have another 1 out of 10. That'd be 1 out of 1,000. So that'd be a 0.1% chance to guess all 3 digits correctly. Okay, now the smudging, if you can kind of make out what digits they could have been, that will improve your chances there. Number 3. You're trying to guess a 3-letter password that only uses the letters A, E, I, O, U, and Y. Letters can be used more than once. That means we have replacement, which means they are going to be independent events. Find the probability that you picked the correct password U. So what's the probability of picking? We want the probability of Y times the probability of the O times the probability of the U is what we want. Probability of Y, we have 1, 2, 3, 4, 5, 6 letters, so that's 1 out of 6. Now the Y is put back in there. So probability of O is 1 out of 6. It's not 1 out of 5. Because remember, things are getting replaced. Probability of U is 1 out of 6. So that'd be 1 out of 216, which is 0.0046. So we got about 0.46% chance, 0.5% chance. Okay. So here's the change in words. Same thing, same setup, but letters cannot be used more than once. Find the probability that you picked the correct password I. So I want the probability of A times the probability of I times the probability of E. They cannot be used more than once. So once you use a letter, it is gone, and you have fewer of them. So the probability of A would be 1 out of 6. Okay? Now we go to the I, the A is gone, we only have 1, 2, 3, 4, 5 letters, so the probability of I is 1 out of 5. The chances of picking I increase, and then the probability I, that is gone, and so that would be 1 out of 4. So 6 times 5 times 4 would be 24 times 5 would be 1 out of 120. Which is 0.0083. It's about 0.83% chance. So you notice with dependent events, the chances of picking it actually went up. Okay, this is this table right here. You're only usually going to use 2 numbers or 2 rows or 2 columns with this. They want the probability that a randomly selected collegiate soccer player is female. So they are randomly selecting collegiate soccer players. So they're just using this column here. They're not using this column. Okay? So it's female. You need the probability of the female over the probability of over the total number of soccer players. So we need the number of female, which is 36,523 over 37,240 plus 36,523. That's your total. So we need the number of female over the total number. I should set it up this way. So we're going to go 36,523 divided by parenthesis 37,240 plus 36,523. And it's about 50% chance. And they're pretty close to each other, so you know it should be about 50% chance. Find the probability that a randomly selected male student is a collegiate basketball player. So this is where we're starting here, randomly selected male student. Okay? So notice they said randomly selecting collegiate soccer player, we're looking at this. Now for a male student, we're going to be looking at these. That's part B. Is a collegiate basketball player. So we want the probability of a basketball player given that he's male. Okay, given that he's male, that's the conditional probability here. So here we wanted the probability that it's a female given that they play soccer. So that's how the conditional probability works with this here. Okay, so what we want is we want the male basketball players over all the males. So that'd be 31,863 over 37,240 plus 31,863. 31,863 divided by 37,240 plus 31,863. And we get about 0.461. So about 46% chance for that happening. Okay, couple other examples from the textbook just to talk through. The example 6 is similar to what we just saw here. So here the probability that a defective part passes. So they want the probability that it's a passing defective part. So the number of defective parts that passed over the total number of defective parts. So 3 out of 39 is what they got there. You look over that example. This formula here comes into play. These kind of have weird wordings. That conditional probability can be written as the probability of both events happening divided by the probability of just the A happening. So how this wording goes, at a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. There's the and, okay? So what is the probability that a student who buys lunch also buys the dessert? There's the conditional probability. So the probability of B happening, given that A is happening, is the probability of A and B. A and B, there's the A, lunch, and dessert. That's A and B. There's the and. That and right there is that and right there. So they give 0.1, 10%, over 0.6, 6%, and they get their conditional probability. So they take the larger percentage, basically, divided by the smaller percentage. Okay? So if you look down at number 7, at a coffee shop, 80% of customers order coffee. Only 15% of customers order coffee and a bagel. There's your and. What is the probability that a customer who orders coffee also orders a bagel? There's your conditional probability. So you're going to take 0.8 divided by 0.15, and that would be your conditional probability. Okay, the probability of them, the first thing, 0.15 divided by 0.8. The and, that's what happened here. 0.1 divided by 0.6, the smaller one divided by the bigger one. The and part divided by just the first part. So the and part here is 15%, so 0.15 divided by the first part, which is 0.8. Okay. So, next page starts it off. So that's 12.2. We will see you soon, and let me know what questions you have as we work through this, and I'll talk to you later.